temperature. So there are several different methods. The first one is called resistive temperature detectors, RTDs. These are essentially resistors made of metals. So I will first show you the relationship, then we will figure out why and how it works. So the relationship here is delta R over R naught equals beta times delta T. So where delta R is your resistance change, R naught is your initial resistance, beta is your temperature coefficient, and delta T is your temperature change. So what this equation is saying is that your relative resistance change is proportional to temperature change. It's proportional. It's a linear relationship, and the coefficient here is beta. So we like linear relationships. It's easy to calculate. And if and on the table on the right, I show you the temperature coefficient of common metals, and they are around 40 times 10 to the 10 to the minus 4, around this the same range. So if you plug your TCR, your beta, into this equation, you will see it's about 0.5% change of resistance per degree C or K, not F. So it's not much change here. Okay, so this is the relationship here, but why does it work? So why does resistance of metals increase with temperature? Why does it increase with temperature? Any idea? So, oh yeah, go ahead.
Is it like more collisions, harder for like your electron mobility goes down?
Yes. Yes, so metal conducts electricity by moving electrons. So electrons moving like in a lattice of atoms. These atoms vibrate around the lattice all the time. So electrons will collide with atoms all the time as they move along. As they move through the metal. That's why there's electrical resistance. At high temperature, the atoms vibrate more strongly. So there's a higher chance for them to collide with atoms. That increases resistance. So, and this is a typical RTD sensors in wearables. We use essentially winding traces of thin metal films of about 50 to 100 nanometers thick. So this is the winding traces. So we have two electrodes, then they connect into like winding traces. But why? Why do we need winding traces? Can we just have a straight trace between these two electrodes? Can we just have a straight trace here?
You need it long enough to actually detect the sizable change.
That's one point. And another point here is, by having winding traces, the resistance increases. We need to have a large enough resistance. Because there's parasitic resistance in our system. Let's say we can easily have like 2 or 3 ohms at our electrodes. So you want your RTDs to have a large resistance so that those parasitic resistance can be ignored. So we want to increase the resistance. And by using winding traces, we can still having a large resistance while keeping the footprint small. And and this pattern also has a low heat capacity because these are, after all, nanometers thin, traces, so they don't take a lot of heat. So this kind of device has a small footprint, has a low heating capacity. This is RTDs. So you will see as temperature increases, its resistance increases linearly, and it decreases linearly with temperature also. This is the first type of temperature sensors. The second type of temperature sensors are by using thermistors or thermal resistors. And there are two types of, at first, these are also resistors. They're called thermal resistors, and these resistors use different materials. They